All right, so I'm a little bothered that this problem is too similar to the one we just did, but we'll have plenty of time to do different ones. All right, so here we go. Our function is f of x equals x to the 2/3, and we want to know if there is a point. We said there was a point. Now let's find it. So this is your starting point when you go to find the point. So f prime of c, we already know, is 2/3 c to the negative 1/3 power. And that equals, well, we want the f of b minus f of a. So let's figure out what that stuff is. So we know that a is 0 and b is 4. So f of a is 0 to the 2/3 power, which is 0. And f of b is 4 to the 2/3 power, which is the cube root of 16. And you could simplify that somewhat, make it 2 cubed root of 2, but I'm not going to. All right, so what we're going to have over here is f of b minus f of a, so cube root 16 minus 0, over b minus a, which is 4 minus 0. Instantaneous rate of change, average rate of change, set them equal. All right, now you typically are going to get some fairly difficult equations over here, so it's going to really draw on your algebra 2 skills. Just rewrite that as a root, this cube root of 16 over 4. There's probably a million different ways you could solve this, but what leaps out at me is we got a bunch of cube roots here. So why don't we just cube both sides of the equation? So we'll just cube both sides and have 8 over 27c equals 16 over 64. And then 16 over 64 we can reduce to 1/4. All right, then I can solve this like a proportion. So 27c times 1, 27c equals 8 times 4 equals 32. So c equals 32/27. Right, and then I just might double check to make sure that the solution I get is in fact within the interval. It is, and that's my solution. All right, there you go. So let's talk about functions that do and do not meet the hypotheses of the theorem. So a reminder, the hypotheses of the theorem, f has to be continuous on the closed interval, differentiable on the open interval, something you have to have memorized. If we do the AP exam in person and you don't have your notes available, they will ask you questions to make sure that you know this and have this memorized. All right, so let's look at some visual examples of cases. Does the function meet the hypotheses or not? Give me a quick yes or no on each of these. Let me give them letters. A, B, C, D. Select all that apply. Which ones do meet the mean value theorem? Take a minute and figure that out. Okay, your minute's up. Oh, hopefully you paused the video. You could have been away for like 6 hours for all I know. All right, so does this one meet the hypotheses? No, because the function, let's call it f, has a non-differentiable point in the open interval AB, all right, because it has a vertical tangent. Remember, if you want to justify that this function does not meet the criteria, you only have to negate one of them. There are two criteria: continuous in the closed interval, differentiable in the open interval. If either one of these things is false, then the mean value theorem does not apply. In this case, it looks continuous enough, but there's a vertical tangent in the interior of the interval. Therefore, this function is not differentiable on the open interval AB. How about this one? No, that should be an easy one because f has a discontinuous point in the closed interval AB. So notice how, even though it's also true that this discontinuous in the open interval AB, this is also true that f is non-differentiable in the closed interval AB. But by writing a closed interval here and an open interval here and a closed interval here, I'm showing that I know that the criteria of the theorem are non-differentiable on the open interval, continuous on the closed interval. Okay, let's look at this one. That is a no, because f is not continuous at A. Therefore, f is not continuous on the closed interval AB, because that point A isn't included in the closed interval. What about this one? That one is a yes. You thought they were all going to be no's, didn't you? This one's a yes. And so here's what I want to be able to, we could just say because the function is differentiable in the open interval and continuous in the closed interval. But we want to discuss the non-differentiable point at the endpoint? Yes, although f has a so I'm showing that I know that f has a non-differentiable point that I should think about, has a non-differentiable point at x equals b, but b is not in the open interval ab. Therefore, f is differentiable on the open interval ab and continuous on the closed interval ab. Therefore, the mean value theorem applies. All right, so that's looking at a function, and just by looking at it, telling if the mean value theorem is met or not. Notice I didn't find, match a function to any of these things. I don't need the analytic function, I just need the graph. And I'm also making certain assumptions. I'm assuming that this non-differentiable point is at the point B because that's what would make it an interesting problem. I'm assuming this discontinuity is at A and not at like A minus 0.0001 because that would be as interesting a question, right? Okay, so next we'll look at some examples from the book, I think. Yeah, next we'll look at some examples from the book.